Okay, hello. This is Gonhee, host of the Enjoying Math YouTube channel, and today is 2025 September 12th. So this is the second video of the Gidesu series, and today, continuing from first Gidesu lecture content, we will keep discussing some foundational topics in set theory with an eye towards rigorous reasoning. If you are completely new to a mathematics major, think of today's goal as learning a precise grammar for functions and sets. Last time, we introduced the image of a function and the pre-image or inverse image, and we practiced translating verbal statements into set theoretical equalities. Building on that, so consider a function, and we talk about basically several things. So let us first set up the following exercises as a warming up. So the exercise, so we consider a function from A to B. And with this fixed function f, we choose arbitrarily subsets on both sides. So we also choose subcollection A1 in A and also subcollection B1 in B. Then we can talk about the inverse image with this B1. So this is defined as a collection in A whose the mapping image belongs to B1, so that we can push this set forward again via the function f. Then it is kind of clear that from the definition of the function, so this set is a subcollection inside of B. But what you can actually see is that this belongs to B1. It's a subset inside of the much smaller subcollection. This is the first statement. And we can also formally talk about the following, the message pull back to the past, the domain, and the push forward. So I intuitively regard inverse image as a past and the image as a push forward, then the set shrinks. And dually speaking, if we start from with the subset A1 and pushing forward and take back, that will give us the following. So if we start from A1, then take the image and take the inverse image of it, then this is sort of the duality principle that we get the reverse inclusion. These asymmetries encode how the function f identifies points, non-injectivity, or the points non-surjectivity. So I highly recommend you to just work on the very concrete examples to observe the concrete the phenomena. So for example, so if you start from the function from R to R, that maps x assigned to x squared and set up the very concrete subcollection, say closed interval from 0 to 1, then you can see that f inverse of this set becomes from the closed interval from -1 to 1, so that if you take the image of it like this, then you can easily check that this becomes B1. So here the equality happens. However, if you choose, say, B1 to be the open interval from -0 to -1 to 0, then you can see that f inverse of B1, this guy, because there is no such function value in this the B1 the range, so that this the inverse image becomes the empty set. So and thus, so the corresponding image should be the empty set, so that this is strictly included in the given B1. So similarly, if we take A1, so what can we take? So for example, let me just naively take -2, -1, 1, and 2 in this collection. Then we can investigate the image of it. So this image should be mapped to 1 and 4, and the corresponding inverse image should be just the same as A1. So here the equality holds. However, if we also take A1 consists of -2 and 1, then the corresponding image should be 1 and 4. And the inverse image of it would be what? So this becomes -2, -1, 1 and 2, so that this strictly includes the chosen sub-collection. So to summarize this, like the fundamental containments, we can just summarize as those two, like the inequalities in this exercise, and try to prove this by yourself. So this is important, like the property. Now let's move on to the very important definition. So the key structural properties are injectivity and surjectivity, or we also very likely formally call it by one-to-one and onto a function. So let's just make the same like the notation. Let f from a to b be a function. So we have the same framework. And we'd like to say f is one-to-one or injective if, so there are several ways to say this. So if f of x1 equals f of x2, this forces the prescribed inputs must be the same. Equivalently speaking, distinct points of the codomain never collide under the function, so that you can take the just contrapositive statement to just change this definition, which should be equivalent. So this property prevents the information loss when moving forward. So for example, so if you just look at two different types of the function, so f of x, say 2x plus 1, this is clearly injective as this is a linear function. But if you take another function as a x squared, for example, then this is not, because f of 1 equals to f of -1. So, and we also will say f is onto or surjective if every point of the codomain is hit. So meaning that, so the image of f that we also denoted by f of capital A is same as b. So that we can draw indeed the naive diagram that f maps to f to this set B, then it fills all points inside of B. So surjectivity ensures that there would be no holes remain in the codomain image. So for example, of course this means the non-example. If you take the domain and codomain to be just a set of the R reals, so if you choose f of x to be x cubed from R to R, this is surjective. Whereas non-example, if you choose exponential function from R to R, this is not surjective, as e to the x is always positive. So no x mapped to the negative numbers. So surjectivity means the image fills all of the codomain B equivalently, and if we say very fancy, every y from the codomain, so we can say non-empty fiber. So this is very fancy, like the term that would be very useful to study topology, geometry, category theory, and like the advanced like level of the set theory later on, but this is not really required, but I still want to just mention some like the term so that we can just say surjectivity means so for each of the fiber, meaning that the collection of the elements in A maps to the prescribed small y. So this is always non-empty. And we will also say for any y, in B, there exists small a in capital A such that f of A equal B. And from here, we will obtain the very natural remark definition. If two properties are satisfied at the same time, let f be a one-to-one and onto function. So of course, f is the function from A to B that maps for each small a to f of A. Then we can see that when both injectivity and surjectivity holds, we usually also call this case to be bijective function or bijective. In that case, every fiber f inverse of y is a singleton set and every element of B is reached. This is precisely the situation where a two-sided inverse exists. So that we can define f inverse that maps from B to A, because for each element small b, we know this can be written as f of A, and such a exists uniquely. So that we can assign each small b to small a. There's a rule, we can definitely do it. And such a function is called the inverse function of the given function, called the inverse function. So if we just stick with the set definition from the first, like the lecture contents, then we have a corresponding set of this inverse function that is the collection of the pair y comma x from B cross A such that f of x equals y. So that's the set description of this like the function. And if you're already a little bit familiar with the university level mathematics, say like the engineering major, so that you can kind of just think the matrix analogy, say a square matrix is invertible exactly when it is both one-to-one and onto as a linear transformation. You can think about it for some of the the audience here. So the intuitively speaking, bijectivity pairs the sets A and B perfectly for each the element A in capital A. There exists unique f of A, and for each element small b in capital B, there is exactly one element in A such that the function value equals to B. So hence we can define the inverse image by reversing this pairing. So this is very intuitive procedure, and if you want to work with concrete example, you can just look at say f from z to z. Z means the set of the integers that maps for each integer to n plus 5. Then you can see that the corresponding inverse image that maps to n minus 5. It's easy, it's important to just you should be able to check by yourself. So formally speaking, so in such a the scenario, you can talk about the composition. So let's also talking about the composition to describe this this inverse image more like a mathematical way. So given two functions, say f from A to B and g from B to C, then we can define their composition in indeed very natural way. So define their composition G circle F from A to C. How this happens? So we know we can map from A to B first, and then we can also map from B to C, so that x should be assigned to f of x first, which should be further assigned by the function g, so that we have a rule to assign from x to g of f of x. So that we just call this by g circle f acting on the chosen x. Yeah, so in set notation, so this can be also written as g circle f. This is the pair consists of x comma g of f of x, that x belongs to A. So of course this is the subset inside of A cross C. Then from here we can describe several interesting functions as exercises. So for example, let us start from two sets. Given two sets A and B in some universal set, then given a function, then first we can describe the identity function with respect to each of the set. So identity function with respect to A is the function from A to A that precisely map for each element to itself, similar to identity function with respect to B. Let me just change the notation so that you can easily distinguish. Then what you can see would be the following. Then one of the benefit for using this like decomposition is that we can now describe injectivity in terms of the composition if and only if there exists one function g from B to A such that g composed by f is the identity function with respect to A. And also we are able to describe the surjectivity f is onto if and only if also this can be characterized in terms of the existence of certain function, but the position to put the composition is slightly different. So such that we now start from f circle g equals to identity function with respect to B. And for this like the lecture, we will focus on the proof of this statement. So not every argument runs, by the way, smoothly without additional principles. So this exercise is actually quite important to see why time to time we need to encounter certain additional axioms. From an axiomatic point of view, you may discover that certain constructions require extra assumptions. Let's try to see this. So proof. So the first part is kind of okay, but let's try to see injectivity implies so-called the left inverse. So you can see that this G, because this G is like the composed in the left-hand side, so that we usually prefer to call it by the left inverse. So we assume f is 1 to 1. So that's our starting point. So that we can draw the knife Venn diagram in the following sense. So we start from set A, and then each element should be mapped via this function f to set B. So each element here should be mapped to f of A. And we didn't assume this f is surjective, so that the set of the image might not be the same as a codomain itself, because there's no such a guarantee. So then how can we now define new function g from B to A again, that if we compose further, then this would be map again to the chosen A. So the way to do is, so from this like the naive like the Venn diagram description, we can see that all we care is just the element of B hid in the image, not the entire codomain itself. So this is the idea. So what then we can do is the following. So pick any element from A. Yeah, definitely we can do this. So the way to do is we can then define one function that depends on this like the selection from B to A. That is, each element should be mapped to two possible scenarios. So if B belongs to the image of F, then we know that there is unique element small a satisfying this property. B should be written as f of A because F is 1 to 1. So that we know such a element A uniquely exists, so that we can assign to small a if B is not inside of the image, then we can just assign to the chosen P. So the all necessary rules, the necessary for defining the function is that for each element of the codomain should be mapped somewhere in the domain. So each element of the domain should be mapped to the codomain. Then, and furthermore, we just need to see why this composition rule should be satisfied. Then actually this is now clear. Then G is well defined. It is clear because each element of the domain is uniquely assigned to the codomain in this situation, and you can see that for any small a in capital A, so if you first start from B written as f of A, then if you just apply the definition of G, then by this rule we know this should be A. This is equivalent to say G circle F equals identity with respect to A. So here now you can see, in order to define this function G, uniqueness provided by injectivity 1-to-1 guarantees G is well defined. So why we need to pick element like a P? Values of G outside of the image never get used when you compute G of f of A. So any fixed like a choice works. So there are implemented such a like a function. So that's why we only claim there exists such a like a function satisfying the composition rule. So this is one interesting like the description and the converse direction exercise. Just by using the definition, you are able to show it. So the second like the part of the exercise, also the reverse direction is it follows from the definition. So it's just an exercise. So just do this by just applying the definition. So the interesting part is this direction that we assume surjectivity that should imply so-called the right inverse, in a sense that this G is now composed on the right-hand side from the F's perspective. So now we'd like to assume if F is onto surjective, then we know that each inverse image of the singleton set Y, or we can simply call again each fiber F inverse of this set is non-empty. But other than that, we never ever said that this like the fiber is the singleton set because this function F is not 1-to-1. So therefore to define a function from G from B to A, we must select a single representative from this like the fiber for every Y in B, ensuring f of G of Y equals Y. So to let you think about this like a perspective, because this is mathematically important for axiomatic point of view. So to define from a function G from A to B to A, so we must choose a single representative G of Y for each of the fiber for every y. Ensuring g of y first and then maps via the function f should be y. However, how do we guarantee that this fiber is not just a finite set? So this selection process across potentially infinitely many non-empty sets is precisely where the global choice principle can be required. So let me just repeat. If we guarantee each of the fiber is the finite set, then yeah, we can definitely choose each of the G of y, single representative. Then as long as the fiber is not assumed to be finite, then there's no way to choose unique element in general. So that's the reason why axiom of the choice is very naturally entered in this like the business. So now you can see that, so given any family of non-empty sets, there exists a function choosing one element from each. With this axiom of choice, then we may pick g of y for each of the fiber to obtain f composed by g equals the identity function with respect to b. And in concrete problems, a natural canonical choice may exist. For example, smallest element under an order, in which case the axiom of choice is not needed. It's unnecessary. So example without the axiom of choice, if each fiber is a non-empty finite subset inside of the natural numbers, then we are definitely able to define G of y to be just either the minimum or the maximum in that like the way. So you can now see that, so this like the direction, we just need to assume, well, this just follows from the axiom of choice if you want to assume it. So that's what we need to cover in this like the lecture. So that, let me just repeat, different global choices yield different like the function, emphasizing that the existence may be non-constructive or non-unique. This observation offers an intuitive like the window into why set theoretical axioms indeed matter. So they tell us which existence claims where we are allowed to make or under what assumptions. So next time we will introduce axioms central to introductory real analysis. So not only the least upper bound property, but before we go that far, we still need to stick with the set theoretical like the object just a bit, including relation, equivalent relation, and partition. That's for the next like the lecture, and that's all for today's like the lecture. Thank you very much for watching this YouTube video, and I will see you next time.